Hello algorithmicians, in this video we will be applying the master theorem formula. The master theorem is a technique, it's like a cookbook, which allows us to find the time complexity of a recurrence relation which splits a problem down into parts and works recursively on those parts. This is the cookbook which you are given in your exam booklet, so you don't need to remember this, all we need to do is apply it. I'll give you a little sense as to what this means to start with. So this first number here is the number of subproblems, and this number here is the size of each subproblem, and this one here is the work done outside the recursive loop. Outside there is a little bit misleading. It's kind of like within each step of the recursive loop, we might say. Okay, we'll see more examples of that later. This video is really just about applying the formula, and this is the easy part of the story, I guess. So we can imagine here we've got some problem set, and we are dividing it, and problem size n. We're dividing it into two problems of n over 2. And we're doing order 1 work within each of these. And then these are all 4 problems, n over 4, n over 4, and so on. But don't worry too much about any of that. We are just following the cookbook. Here we go. So we need to identify first what A, B, and C equals. So A equals 2, that's this one here. B equals 2, it's this one here. C is slightly less obvious. If we refer to this as k n to the c, well, this is clearly 1 times n to the 0. So this isn't, the 1 there is not a function of n, it's in constant time. So we say here that c equals 0. Next, we consider the right-hand conditions of our of the recurrence of the master theorem. Right, b to the power of c, so 2 to the power of 0 equals 1, and we can see then that 2 is greater than 2 to the power of 0, i.e. a is greater than b to the power of c, so we are working within case 3. Worth noting that these cases, and in fact the theorem itself, are slightly different from other things you might see on the internet. So this is really good for people doing VCE algorithmics. It might not be fantastic for you if you're doing a different course. And likewise, if you're doing VCE algorithmics and you see a slightly different formula, use this one. So we are order of n log b a, which is order of n log 2, which is order of n to the 1, or just order n. Nice. Now, at any point, start to try these out yourselves. Pause the video, and write down what does A, B, and C equal. We should have A equals 4, B equals 2, C equals 1, because this is n to the power of 1. This would be the same, by the way, if I put a 5 here. That wouldn't change that c is still equal to 1. Then we consider which case are we interested in. B to the power of c equals 2, and we can see that a is greater than that. A is greater than b to the power of c, so we are doing case number 3 again. So this is O of n log 2 of 4, which is big O of n squared. Next one. Write down A, B, and C. A equals 8, B equals 2, C equals 1. Now pause and decide which case are we talking about. We've got b to the power of c equals 2. So once again, it's case 3. A is greater than b to the power of c. So we're dealing with case number 3. Big O n log 2 of 8. So this is order n cubed. Big O of n cubed. Next one. Try this yourself. A equals 8. B equals 2. C equals 2. We have A is greater than B to the power of C. Hence we are on number 3. So this one is still. Do I mean still? Yes, I do, because it's big O of n log 2 of 8, which is big O of n cubed. What's next? I think actually this is going to be the same as the previous one, so let's try and find one that's a little bit different. Write down A, B and C. We have A equals 4, B equals 2, C equals 2. In this case we have A equals B to the power of C. So we are applying number 2. We have big O of n to the power of C, so n squared, times log n. Try this one yourself. We have A equals 3, B equals 2, C equals 3. We can see A equals 3, well, no, no, A equals 8. We can see that A equals B to the power of C, case number 2. So we have big O of n to the power of C, so n cubed log n. Next one, we have A equals 1, B equals 2. Now we know that we could complete the square and write this as a quadratic, so it's the highest power of n that we're interested in. C equals 2. So in this case we have A is less than B to the power of C. So we're dealing with case number 1. And this one is just going to be big O of n to the power of C. So big O of n squared. Last one. It's a bit of a funny additional function there, isn't it? So A equals 2, B equals 4, C equals a quarter, because it's n to the power of a quarter. So once again, we have A is greater than B to the power of C. You can check on the calculator if you're not entirely sure. So we are dealing with case number 3. So this gives us big O of n log base 4 of 2, which is big O of n to the half, which is big O of the square root of n. Okay, the next video we see on this is going to be how do we read off the values of A, B and C. How do we work out what the recurrence relationship is, which is much harder. But hey, at least now we know how to use the cookbook.